Hello friend. In the previous modules, module number 6, 7, 8, we have seen the activities carried out during the clinical phase of bioequivalence study, bioanalytical phase of the bioequivalence study, and also we have seen some of the activities like pre-study activities. Now, we are going to see how the pharmacokinetic and statistical analysis is carried out after we get the plasma concentration data from the bioanalytical laboratory. When it comes to pharmacokinetics, we need to understand some of the terminologies and definitions. So here, AUC is the area under the curve. AUC 0 to infinity is the area under the curve extrapolated to infinity. For example, we are going to measure the AUC 0 to t first, that is the time 0 to the last measurable time point in the entire collection of time points. From there, we will extrapolate using the elimination rate constant. If you add the extrapolated value, you will get the AUC 0 to infinity. Then when it comes to the steady state, there will be AUC 0 to 2, that is nothing but the AUC between the dosing interval. And C tau is the minimum concentration at the dosing interval, that is likely to be the last time point. And then we have C average SS is the average plasma concentration at the steady state. Now comes the Cmax, which is the maximum plasma concentration. Then Cmax SS, it is the maximum plasma concentration observed during the dosing interval at steady state. And the Cmin SS is the minimum plasma concentration observed during the dosing interval at steady state. Then we have the PAUC, that is nothing but the partial AUC or a AUC between the two specific time points, you can call it. So some of the dosage forms like some extended release, delayed release dosage forms, these partial AUCs are used based on the design of the extended release dosage form. Then we have lambda Z or KEL, that is nothing but the terminal or elimination rate constant, and the Tmax is the time to reach maximum observed plasma concentration. Then finally the Toff, that is nothing but the half-life, which is calculated from the elimination parameters. This particular slide representing the diagrams of a typical oral pharmacokinetics from a oral dosage form. So once you have the oral dosage form, the drug concentrations rises from the baseline since it is starting getting absorbed in the gastrointestinal tract. So from here, from the baseline, the drug concentration starts and rises to the maximum level, that is called Cmax, and this is the time to reach maximum concentration. Then it started to decline because the drug elimination happens parallelly along with the absorption, and it starts eliminating and comes to the baseline again. So here we have Cmax and the Tmax. This is the time to reach maximum concentration, the maximum concentration observed in the graph, and you have the AUC you are being calculated. From here you have the trapezoid, you can apply the trapezoid. Each and every trapezoid areas are calculated, and the two triangle at the initial and the last phase. If you cut a line here, put a line here, it is a triangle, and you put a line here, it is a triangle. So two triangles and trapezoids used to calculate the entire AUC. And this particular diagram clearly shows the absorption phase of the curve and the elimination phase of the curve, and the TF is also mentioned here. It's time at which drug has lost half of its maximum concentration. That is what here it is defined, and it is already we explained how it is being calculated. This is the Cmin, which is observed in the particular plasma concentration profile. This is the typical oral pharmacokinetics diagram of a steady state or a multiple after getting a multiple dose of the drug administration. So here this is 0 to 12, 12 to 24, like that it is mentioned. So it is every 12 hours the dosage form is administered. Here you can see 0 to 12 hour, 12 to 24. So every 12 hours the dosage form is administered. This is the first dose. This could be the first single dose pharmacokinetics you can consider. And if at all, if you are leaving without administering the further doses, this is how the plasma drug profile will be looking like. And from here you can extrapolate with the to the infinity level. So that is what here dotted line is showing. And after the multiple dose, it reaches steady state here. In this, after 72 hours, it reaches the steady state where you have the steady state maximum and steady state at the dosing interval, that is called C tau SS. This is the maximum concentration observed the steady state, and this is the area under the curve between the dosing interval, that is the tau. So these are the critical parameters observed in the steady state pharmacokinetics. Also explains the similar parameters, but at the range of minimum effective concentration and minimum toxic concentration. This is the minimum toxic concentration. Above this, the toxic effects or the adverse event likely to happen. And this is the minimum effective concentration. During the steady state, the effective concentration is maintained. That is the whole objective of doing the multiple dose administration. And this is the peak Cmax SS. This is the AUC, and which I already discussed, and the C trough or C tau at the concentration minimum of the dosing interval. This is the CSS average, that is the mean. All the parameters are clearly defined in this particular diagram. So when it comes to the pharmacokinetic and statistical activity, so during the study, the first activity will be the randomization generation, which happens from the pharmacokinetic and statistics department. A statistician will generate the randomization schedule for the clinical study. So how it is randomly assigned? So that is what here we are seeing here. So this is three treatment and three sequence. You can see A, B, C, B, C, A, C, A, B. Like so, there are three sequences used in this particular randomization, and each subject has been exposed to three sequences and it is randomly assigned. So this is the typical randomization schedule which is generated for the clinical study. And here it is explained how subjects are assigned to different sequence. For example, if this is the two sequence, this is the randomization, two sequence AB or BA or reference test or test reference. So this is the period 1 and period 2 two-way crossover study where first reference will be administered, then washout period comes, then test will be administered. Then it will be vice versa, test followed by reference. So these are the sequence will be assigned to the each and every subject so that he will be exposed to both the treatments with a washout period. The same thing explained here, how the different sequence will be used for the four-way crossover study, TR-TR and RT-RT. These are the two sequence and used for a four-way crossover study and with different washout period in between each and every treatment. Here is the pharmacokinetic analysis happens. This we already seen briefly in some other module, but still we are going to see in a detailed manner where the pharmacokinetic analysis starts with the QED concentration versus time data. So this will be obtained from the bioanalytical department, and this analysis will be carried out by the software called Winolin or some other software. SAS also you can program and do, or you can do manually by using Excels and some other platform. So this concentration is a time data and randomization schedule of the BE study will be used to prepare the input data first for the study. Then the input data will be QC'd and QA'd. Then the input data will have variables like subject, period, treatment, sequence, time point, and concentration. This is what very critical. You can see this is how it will be aligned. You will have the sequence, you will have the period, subject, time point, and concentration. All this will be tabulated in Excel, and it will be QC and QA. Quality control and quality assurance check will be done, and that will be taken as the input data for the pharmacokinetic analysis. So the input data will be analyzed using the software, and subject wise, treatment wise, and the data will be tabulated, and the graphical presentation also will be prepared like semi-log and linear plots. And then the tabulations will be prepared with all the summary statistics like mean, standard deviation, percent CV, minimum, maximum, etc. That for each and every parameter it will be prepared and tabulated. So here are some of the softwares used for the pharmacokinetic analysis, like Phoenix, that is what called Winolin earlier, but now it is Phoenix Pharmacokinetic and Pharmacodynamic Platform version 8.3 is the latest one, and we have some software like Thermoscientific's Kinetica, PKPD data analysis, simulation, and for the simulation and reporting system. So this is also can be used, but the widely used one is the Phoenix one. And also we have pharmacokinetic and pharmacodynamic modeling in symbiology by Maxwork. And finally, we have statistical analysis software SAS Institute by the SAS Institute. We can program all the mathematics into the SAS software and we can calculate the pharmacokinetic parameters. So now we have done the pharmacokinetic analysis. We have all the parameters like Cmax, AUC, T of elimination rate, constant, AUC infinity, etc. So now we have to do the statistical analysis generally for the primary pharmacokinetic parameters for which the bioequivalence need to be established. So primary pharmacokinetic parameters like Cmax, AUC, T and AUC infinity, or in case of steady state Cmax SS, AUC SS or AUC tau and C tau or C min SS, or all these parameters will be tabulated and then used for the statistical analysis. So the bioequivalence analysis, we used to calculate the 90% confidence interval for the bioequivalence conclusion, and then we carry out the ANOVA, analysis of variance, for seeing the effect of subject by effect of sequence, effect of all these variables, whatever variables used for the analysis, we have to see the treatment effect, how significant it is, all those things will be assessed through the ANOVA analysis. So the input data prepared with variables like subject, again subject, period, treatment, a sequence along with the primary pharmacokinetic parameters values. Then the input data will be processed to get the output data. So it is a program which will be running and give you the output data. So the PK parameters, whatever Cmax, AUC and AUC infinity, whatever we are using, it will be log transformed during the process. So hence the 90% confidence intervals is set at 80 to 125% to conclude the bioequivalence. This statistical analysis can be carried out by the Phoenix software also. Once you complete the statistical analysis, immediately you can check the bioequivalence by using Phoenix or Windowlin software, and you can use the SAS software by the SAS Institute also. This is how a typical summary statistics of the pharmacokinetic parameters will be shown in the tabulations. You can see some other representations, but this is how it will be presented generally. Cmax, AUCT, AUC infinity, and all other parameters like T of some other parameters also included here. But in case of bioequivalence, generally it will be 6 parameters: Cmax, AUCT, AUC infinity, Tmax, elimination rate constant, and half-life. So these are the 6 parameters. 3 primary and 3 secondary parameters will be reported. This is what the mean and standard deviation values they are given. And you can have some in the summary statistics like minimum, maximum, percent CV, etc. That is how it is being presented for different strengths. This table showing the different strength, but generally it is test and reference is generally presented in the bioequivalence study. This is the summary of statistical data representation. Generally, for each and every parameter, mainly the primary pharmacokinetic, Cmax, AUCT, and AUC infinity. Cmax, AUCT, and AUC infinity. The T by R ratio will be presented. How close to each other, the test and reference, how close to each other, that will be represented by T by R ratio. And you can see the 90% confidence interval. So this is the bioequivalence results. It is passing the bioequivalence. And here the typical example of the graph where you will have the plasma concentration profile close to each other, which is concluding the bioequivalence. So this slide presented the linear plot as well as the semi-log plot, which is used for the presentation of the pharmacokinetic data in the submission of bioequivalence studies. So this is typical linear plot where you have the concentration in the y-axis and the time in the x-axis, where the test and reference products are being presented with the standard deviation, and standard deviations are represented by the error bars. And in this side, on the right side, you can see the semi-log plot where the y-axis is log transformed and the x-axis is not log transformed. So typically the semi-log plots are used to calculate the elimination parameters. So with this, we have come to the conclusion of how the pharmacokinetic and statistical analysis are carried out in a brief manner. And in the next module, we are going to see the report writing process. Thank you.